Okay, so now we're here with another question. Two bouncing balls. Specifically, there are two balls are projected with different horizontal velocities, right? But they're purely horizontal, and we are asked to find, based on this diagram, right, the ratio of the velocities, the position of the vertical post, as well as the height of the vertical post. Okay, so let's start off with um the ratio. So I didn't put an answer for this one right here, right? And I'll be going through it because if you know the answer, it's quite clear. It's a big hint for what you need to look out for, right? So unlike some of the answers, so unlike some of the questions where the answer doesn't really tell you much about the process, right? In this case, the answer would tell you, so it would be a spoiler of sorts. Okay, so let's take a look at the diagram first. First we note that since we want to find the ratio of v1 over v2, right? So the first ball is projected with v1, the bigger velocity is v1, and the bigger velocity here is v1 and the smaller velocity is v2. So we're going to find the ratio of the velocities. How do we find the ratio of the velocities? We can observe that since the velocities are purely horizontal, right, the initial vertical velocity are both 0. So the time taken to fall to the ground, right, to the ground is actually going to be the same, right? So if the time taken to fall to the ground is actually going to be the same, right, meaning that both balls hit the ground at the same time, just at different locations, but they hit the ground at the same time, then the ratio of the horizontal displacements, the ratio of the horizontal displacement would be the ratio of the velocities, because because horizontal displacement equals to the horizontal velocity times time, and we know time for both is the same, right? So we just need to find the ratio of the velocities. We just need to find the ratio of the horizontal displacements. So in order to find the ratio of the horizontal displacement, what we need to do is we need to understand that projectile motion is reversible. What does that mean, right? In other words, what do I mean by so-called reversible? Or rather, it kind of repeats itself, right? What I mean by that is that if I look at the green path, right, the second ball, right, ball 2 with velocity v2, it falls down the green path, right? And after that, it bounces back, right? What does it bounce back? It bounces back and follows the yellow path, okay? It follows the yellow path, right? But because the horizontal velocity has not changed throughout this time, right? The horizontal velocity has remained constant, right? The horizontal displacement of the green path and the yellow path must be the same, right? Because they reach the same height, right? So if the vertical velocity purely flips when it hits the ground, right? So the time taken for it to fall during the green path is the time taken for it to rise during the yellow path. So displacement, the horizontal displacement of the green path must be equal to that of the yellow path, right? Then lastly, right, we also have that the horizontal displacement of the yellow path must equals to that of the orange path, because it's a parabola and the parabola is symmetric. Okay, so what we have is that the green path's horizontal displacement equals the yellow path horizontal displacement equals the orange path horizontal displacement. So we get that displacement for the second guy, right? Displacement for the second guy, um, at least the green path alone, right? I'm going to highlight it in green. The displacement for the second guy, green path alone, is equals to 1/3 of r. Okay, because the green plus the yellow plus the orange is total r, and all of them are the same, right? So since x2 is equals to 1/3 of r, that must tell us that the velocity of the first ball over the velocity of the second ball, right, is equals to 3, right? The red arrow is 3 times longer than the blue arrow. So the first answer is going to be 3. The ratio is 3. Okay, so now I'm going to clear the screen and put the picture again, right? So we have a clean diagram. And what's the position of the vertical post? Okay, so this one requires a bit further analysis. So previously we analyzed the horizontal ranges, right? So what's the thing to analyze in question B? The thing to analyze would be the time, right? The time taken for the balls to fall, right? So what's one observation? Okay, what's one thing we already know? The thing we already know currently is that the the first ball, right? The first ball which follows the red path, right? The first ball which follows the red path has horizontal velocity of 3 times bigger than that of the blue path, right? The blue path, horizontal velocity of the blue path is 1/3 of that of the red path, right? Okay, so based on that, right, we know that the vertical velocities, they start out both at 0. So at any point in time, right, they fall, the height at which they fall, right, the height is always the same, right? At least until the first guy hits the floor, right? At least until they hit the floor, then the first guy starts to bounce back up, whereas the second guy stays here. So the height when they start to fall, the height during the I'll put it in orange. The height during the orange motion, right, of the two balls is always going to be the same, right? Height is always going to be same throughout the motion of the throughout the two orange motions. The height is always going to be, they're going to fall at the same height, at the same, their height changes at the same rate. Okay, so what does that tell us about this? What is the post defined by? The post is defined by some height, right, which we currently do not know. But what we do know is that when the first ball, the one that goes faster, when the first ball hits the post over here, when it touches the post at the tip, just glances the post, right? Then the second ball, what's the height of the second ball? It's also going to be here, right? It's also going to be here. Okay, we don't know where that is horizontally at the moment, right? But we know it's also going to be here, right? And so what is the horizontal position? The horizontal position of this, right? If I draw a red line down, the horizontal position of this, we know the ratio of the velocities, right? So the horizontal position of this must be 1 over 3 xp, okay? And so from here, yeah, so now we do know the horizontal position, right? Then what else do we know? We know that the yellow path, right? We know the yellow path horizontal displacement is equals to that of the green path, right? Because it's it whether you fall down or go up, right? The horizontal displacement must be the same, right? Because it's the horizontal velocity hasn't changed even after the bounce. So we know that between 1/3 xp and xp, right, this thing bisects it in half, right? So what that tells us is that the position here is actually 2/3 xp. Okay, so that's cool. Where does that bring us now? Okay, so we want to find the position of xp in terms of r, right? We want to find the question they give us r as coordinates, right? They want us to find xp in terms of r. We have a hunch that it looks kind of like half, right? But at the moment we haven't proved it yet. So how do we prove it? We need to observe that the motion of the second ball, the slower one, it can be kind of broken down into 6 phases. Okay, it can kind of be broken down into 6 phases. Namely, the first phase is this, right? The second phase is this, the third phase is this, right? The fourth one, I'm going to highlight in a different color now, is going to be the yellow one, right? From the post to the peak, right? Then the fifth one is going to be from the peak to the height of the post again, right? The height of the post again. And the sixth one is going to be that height of the post down to the floor, right? So we use the fact that parabolic motion on the way down to the way up, right, and back down again is very, very kind of symmetric in nature, right? We use the fact that parabolic motion is very symmetric about the peak, about the bouncing point, and yeah. So we use that fact and we realize that when it's falling, right? When it's falling, number 1 over here and number 5 over here, right? The green one, number 1 and number 5 is actually the same, right? In terms of horizontal displacement and trajectory, it's just a translated version, right? And we also use the fact that number 2 and number 6 over here are also the same. They're just translated, right? And hence, if we know number 1 and number 5 is the same, and number 2 and number 6 is the same, then that tells us that number 5 is also of length. Horizontal displacement during number 5 is also 1/3 of xp, and the horizontal displacement of during the 6, right, the blue one, is also 1/3 xp, and that tells us that and lastly, we use the fact that the green one and the yellow one is the same, right, because it's symmetric about the peak, right, the peak of the parabola over here. So the yellow one is also 1/3 xp. So basically, this is now all these are 1 over 3 xp, right? All these are 1 over 3 xp in length, right? So you can see that on the left over here you have xp, on the right over here you have xp, right? And up, because we decompose the right one over here into 3 motions, and we prove that all of them are symmetric, right? There's a lot of mirroring of the motion as well as translating of the trajectory, a lot of such patterns, and there's a lot of sequences you can go through. Maybe 1 and 4 you can observe that it's the same also because it's symmetric about this bouncing point, right? There's a lot of such you can go through, but any one of them would work, and you can convince yourself that 4, 5, and 6, right? They span xp in total, right? So that means that xp must equals to half r. Okay, so xp is equal to half of r. That's the position of the vertical post. Okay, so if not, let me just clear the screen and post one more time, and we go through part C. So part C, right? What is it to consider in part C? Part C is quite simple, right? Namely, we know that the time of flight, right? Now we know the time of flight of the red path, right? Because remember, horizontal velocity doesn't change, right? So the time of flight of the red path and the orange path, right? The orange path, the time of flight of these two are the same, right? So that means, and yeah, so the time of flight is the same because xp is half of r, and that will mean that the vertical velocity, right? Remember, is half gt squared, right? The vertical displacement is half gt squared, right? Or rather minus half gt squared if you take upwards as positive, but it's gt squared, specifically is t squared. So if you wait for some duration t1 over here, right? If you wait for some duration t1, then it's half gt1 squared. Then if you wait for twice the duration, then it's going to be 4 times. So we know that this displacement over here from starting, right? From starting to r, I'll highlight it in green. From starting to r, this is essentially 4 times, right? 4 times that of the starting to the post, right? Which I'll highlight in purple, right? 4 times of this, right? And hence, the height of the post will be equals to 3 over 4 h. Okay, so I hope so the answer is 3 over 4 h. I hope that this question gives you some intuition about the symmetric properties of parabolic motion. Specifically, it's symmetric about the bouncing point, it's symmetric about the peak, and when two objects with different horizontal velocities fall, right? Because the vertical velocity is initially the same, and they have the same acceleration, they're gonna fall at the same rate, right? So when this guy is at this height, this guy is at this height, right? When this guy is at this height, this guy is at this height. So we're using all these symmetric properties to show these 3 results. So the first scenario we consider first so altogether the lessons to learn from this question is part A, right? We consider horizontal displacement, consider x, right? The x displacement, right? When it hits the ground, right? When hit the ground. Okay, then for part B, we consider all the symmetric things, right? Consider the time taken, the time of flight, right? The time of flight, right? Consider the time of flight and how the 2 objects fall at their heights decrease at the same rate, right? Their height is always in sync, at least until they hit the floor, right? Consider the time of flight as well as I'll say symmetric properties of parabolas. Okay, and part C, I'll just say it's half gt squared, right? It's the understanding of half gt squared. Okay, so yeah, with that, I'll see you in the next question.